This is a multiplication table. Is this what you got?
Yes.
Yeah.
Yeah.
Okay, cool. Now, something totally different. Could you tell me what's the last digit of this addition? Of
2.
this? Sorry, who said 2?
Sophie.
Sophie, okay. Could you tell me your reasoning?
Because it's 12, so then it'll be 2.
Sorry, did you do the sum or what did you do?
Sum 4 plus 8 is 12.
Oh, sorry, you didn't do the sum of those two numbers.
No.
What
But you
did you
don't
do
need to.
first? What did you do first?
I just took the last number of both. and
Okay,
then
so
just-
you look at the last two digits.
Yeah.
And you did the sum, and then you look at the last digit of the sum, no?
Yeah.
Okay. Okay, somebody that is not Sophie, could you tell me the last digit of this?
5.
Nicole, why is 5? What did you do?
Because you do 7 times 5.
You look at the last digits,
Yeah.
and then you look at the last digit of the product, no? Agree?
Yeah, I agree.
Okay, now, could any of you tell me how is this related to modular arithmetic?
Is this mod 10?
Indeed, this is modulo 10. And back, I don't know if you know, the metric system comes from the French Revolution. They wanted to do everything in multiples of 10, and they proposed this clock with 10 hours and 100 minutes per hour, and I guess 100 seconds per minute. But it didn't catch because there was a de facto standard, I mean, the clock that we use even now with 12 hours and 60 minutes per hour. But modulo 10, 0 denotes multiples of 10, 1 denotes multiples of 10 plus 1, and so on. But do you see the pattern, I mean, of the relationship between the digits that we use, I mean, the remainders and the numbers they represent? I mean, 8 denotes 8, 18, 28, 38.
They all
Five-
end,
sorry.
all end the same number. They all end in 8 in number.
So it's the last digit, no?
Yeah.
So n is the same as the last digit of n modulo 10. Okay, and this is a modulo 10 addition table where it's the same as the last digit arithmetic that you were using, okay? And for the multiplication, it's the same. Okay, when you are operating modulo 12, you just look at the last digit. Okay, now, do you know the criteria? I mean, how do you decide if a natural number, well, or an integer is divisible by 9?
If it all adds up to 9, or if all the numbers that are in it add up to 9.
The digits, no?
Yeah, if they're divisible by 9. Like if what they add up to is divisible by 9, then
okay. Does any of you, I mean, is any of you able to explain why that works? I'm going to explain you using modular arithmetic. So, and for this, we're going to use modulo 9. What happens is that 10 is the same as 1 modulo 9, no?
Yeah.
You agree? Okay. And then, well, I haven't proof in general, but, well, 100, what is 100 modulo 9?
1.
Because
99 is
plus 1.
1 less.
Okay. What about 1,000? Somebody different than Taken. What is 1,000 modulo 9? It's 999 plus 1.
It's 1.
And 1 million.
1.
Yeah, all the powers of 10 are 1 modulo 9. Okay. So for any, I mean, what I'm talking about obviously, yeah, here I'm referring to n natural number, no? So, well, including zero, so 10, 100, 1,000, any power of 10. If you subtract 1, you get 9999999, which is obviously a multiple of 9. So all of them are 1. Okay, what happened? Because we work on the decimal system, whenever you have a number, I mean, what do we mean by 8,794? What we mean is 8,000s, 700s, 9 tens, and then 4. Okay? And when we put our special glasses, modulo 9, what happens? The 1,000 becomes 1, the 100 becomes 1, and the 10 becomes 1. So that is congruent to 8 plus 7 plus 9 plus 4, modulo 9. Do you understand?
Yeah.
So that explains why, I mean, if the sum of the digits is multiple of 9, the number is multiple of 9. But actually, this is a stronger statement. This is saying that the remainder of n when you divide by 9 is the same remainder when you divide the sum of the digits. So for example, if you have 20, the sum of the digits is 2, and the remainder when you divide 20 by 9 is 2. Or give me another number, I mean.
13.
13. 1 plus 3 is 4. Well, and then 4 is the remainder of 13 divided by 9. Well, if we use a larger number, let's say 87, then you would say 8 plus 7 is 15, and then you could apply the same thing again. 1 plus 5 is 6. So the remainder when you divide 87 by 9 is 6. Okay? But in particular, if the sum of the digits is multiple of 9, then n is multiple of 9. Well, and it's a if and only if, so it's a necessary and sufficient condition, okay? And given that 10 is also 1 modulo 3, you can use exactly the same argument to prove that the n is congruent with the sum of its digits modulo 3. Okay, I mean, the divisibility criteria by 3 is the same. You take the sum of the digits and you check if that's multiple of 3. Now, does any of you know the criteria to check if a number is divisible by 11? I suspect that they took this out of the curriculum some decades ago. So you don't know? Okay, but we can do something very similar to what we did with 9. For 9, we said, what is 10 modulo 9? And we said it's 1. So what is 10 modulo 11?
4. Oh wait, no,
Sorry?
10 more. Sorry, no.
10.
10.
Okay, but that's not really useful to say 10 is 10. Is there something else that you could say that is you think could be more useful?
-1.
1.
Sorry, Take?
-1.
10 is the same as -1, modulo 11. So then what happens with the powers? And I haven't proved to you, but you can, in modular arithmetic, you can take the powers on both sides. So, I mean, you can square both sides. So 10 squared is 100, and -1 squared is
1.
1. And 10 to the cube is 1,000, and minus 1 to the cube is,
-1.
so in general, for the even powers, 10 to when n is even, 10 to the n is 1. And when n is odd, 10 to the n is -1. So then, what you do in this case, if, let's say, you want to check if 38,794 is divisible by 11, well, you write it this way, I mean, explicitly, well, this way, because that we use the decimal system. And then you put your classes modulo 11, and what happens is that 10,000 becomes, well, that's 10 to the 4, that becomes 1, 11, 1,000 becomes -1, 100 becomes 1. So then you have this so-called alternate sum. So for 9, you add the digits. Here, it's like you start with positive, and then the next one is negative, next one positive, next one negative, next one positive. You see? So n is divisible by 11. Well, n is congruent to the alternate sum of its digits, modulo 11. And in particular, it's divisible by 11 if and only if the alternate sum of its digits is divisible by 11. And yeah, and if you are not looking for the remainder, I mean, you can start with positive on it. Okay, so then, okay, we have a few minutes to practice this.